Good evening, everyone. My name is Ferran Garcia Pichel, and I'm the Dean of Science in the College of Liberal Arts and Sciences, and I'm going to try to get this festivity going in a little bit of order, if we can. What a fantastic evening today to come here to celebrate the choosing of two missions, not one, in the Discovery series. So we're very happy to do that. One of them is, as you know, Psyche, and the other one is Lucy. So before I get started a little bit with a few words, not many, because we have to keep that under control, let me recognize a few people. First of all, let me recognize Susie Marston, who is here and who has made this fabulous facility of the Marston Theater possible for all of us to enjoy. I'd like to so thank you, Susie, as always. I'd like to also recognize elected officials who are here accompanying us today, and take the opportunity also for thank you for your support, and thank you for sharing this evening with us. I hear also tonight with us in attendance is co-chair of ASU trustees, Laura Roskin. Not sure I see her, maybe she's coming a little late, and ASU trustee Doug Fulton. Thank you for being here with us tonight. I think perhaps for some in the audience today, this is the first time we hear about the two missions we're thinking about tonight, and let me say a few words about what each one of these two missions is about. So the Lucy mission is a mission which is going to visit Jupiter's Trojan asteroids. This is a group of a few thousand asteroids. They're rather small bodies compared to the main planets that are intriguing in many respects. And so we are going to send from ASU's part one particular instrument that will be developed here. That is the thermal emission spectrometer, with which we will take pictures of those asteroids in order to find out things related to its thermal components. The mission, incidentally, but not non-trivially, I would say, is named aptly after Lucy. Lucy is one of the fossil hominins from, I think, the Australopithecian. I'm not sure exactly what the adjective would be here. That's an Australopithecine afarensis fossil, who's was discovered by Don Johansen, who's I hear also in the audience tonight. Okay, right by Sue. Oh yeah, there he is. So, and then the Psyche mission is again our first ASU-led deep space mission to the aptly named Psyche asteroid. I wonder why it was named Psyche after the mission. So the asteroid is a strange asteroid that's completely made up of metal, iron nickel metal, and we think, or some of us think, that it may be a remnant of a planet core. So these are the two missions. In a way, it is interesting to realize that the two missions are not to some of the major sort of well-known planets, but are both geared to rather inconspicuous, rather small, also strange and mysterious bodies. And I think this is a daring couple of missions in that regard. And we have to, so many times in science, we get most of the information from things that are not very obvious and from things that are a little bit strange, mysterious, that are a little bit deviating from the norm. And this is the case for these two groups of asteroids. And so anyway, I like to remark how daring our group of scientists here has been, but also NASA in choosing those two missions. has been equally daring. I think there is much to be gained in these missions. And so, as a relatively young university, trying to lead the way in terms of space exploration and so on, we're really excited about doing a good job on those missions. It doesn't really come on a vacuum. Let me just tell you a short story about exploration and Earth and space exploration. That is something that is been in the soul of Arizona for hundreds of years. From some of the best Native American scouts that explored around in the U.S. Southwest to 300 or more, 320 years ago, the visits of one of the most famous Arizonans, Eusebio Kino, who was a Jesuit priest that came from the South in a mission of exploration. And he was a person that was not just a cartographer, which he was, and a geographer on a mission of discovery to try to find the land pass to California from Mexico. But also he had an idea that California was not an island. And in his discovery, he also made some of the first astronomical discoveries made in Arizona. In one of his trips in the mountains of Yuma, he described in 1701 the first asteroid to be seen in Arizona, and in a published work that he published later in the mountains near Yuma. So from those roots and that mindset of discovery, of exploration that went on through the ages in this state, this university sprung up, and it's kept that momentum, and it's now embarking on one of the biggest missions again. And so it's really a wonderful evening to celebrate in this regard. So tonight we have a couple of very distinguished guests here to help us out, and then a panel. And so without much ado from my side, let me introduce Michael Crow, who is here. Michael M. Crow is an academic leader, an educator, designer of knowledge enterprises, and science and technology scholar. He became the 16th president of Arizona State University in July of 2002 and is guiding its transformation into one of the nation's leading public metropolitan research universities, an institution that combines the highest levels of academic excellence, inclusiveness through a broad demographic, and maximum optimized societal impact, a model termed as the New American University. Michael.
Thank you, Ferran. I'll be quick. First, congratulations to the team. Congratulations to NASA for its wisdom, its insight, Thomas, its perspective. Congratulations to the American people, who are still willing and happy to spend billions of dollars a year of their hard-earned resources because they feel in their inner spirit the same thing that all of us in this room feel, and that is we want to know. We want to know everything. We want to know who we are, what we are, where we came from, how it happened, where it came from, where we might go, how we might get there. Because by nature, in our bones, in our brains, in our fabric, we are all explorers. All of us. Whether we're the scientists that are designing this, or the engineers that are building it, or the managers who are making it all happen, and it takes all of that to make it come together, we want to know. We want to know. So this mission, Psyche, you can look the word up. It's a fascinating word with lots and lots of different histories, but it's got this Greek origin to it, this sort of breath of life. And so I'm not sure exactly what it meant then or where it was derivative of even before that, but there's this notion about going back to point of origin, going back to how did it happen or what happened. And we think we know, and we know a lot, but I don't think we know as much as we think we do. And so I started thinking some time ago when I joined the faculty at Columbia University in 1991, when I became executive vice provost there and the chief research officer there, I started wondering why it was that so few kids were taking science as a major if they weren't going to medical school. was like weird to me. And then I realized it was because the scientists were kind of boring. And I got to know them after a while, and I thought, not only are they're boring, but they're sanctimonious. So they're sanctimonious. It's not a lecture, Phil. And so they're sanctimonious and boring, and not all of them, obviously. Some of them are great and inspirational and all kinds of other things. And a lot of people are just naturally inspired by science, but it turns out most people aren't. They're inspired by exploration. They're inspired about solving problems. They're inspired about understanding and knowing. They're not so much inspired by organic chemistry. And so one of the things that a group of us decided to do when we were able to come here to ASU was to say, well, how do we make all this more exciting? And so one of the things we started doing, and I'll just sort of add this as a point, is rethinking our own intellectual design. So we now have science schools here and science programs at ASU that do science for the sake of knowing, which is fantastic. We have science schools that are science schools driven on actually working to solve a particular problem, like our School of Sustainability. It's an outcome science. We obviously have engineering schools that build things to solve particular problems and design things to make things happen. And then we have this school. The School of Earth and Space Exploration is built on that spirit of that idea of exploration. Now, some of you that have been on the faculty for a while will be shocked when I tell you that we have just under 30,000 STEM majors at ASU. Think about that. 30,000 STEM majors at ASU. That's more than a 2.5-fold increase in the number of STEM majors. In engineering alone, we've gone to 20,400 engineering students with grand challenge schools. And so what we learned in this lesson, for those of you that wondered what knowledge enterprise architect is all about, if you want an outcome for a civilization or a society, then you need to organize yourself to move towards that outcome. So if we want a sustainable interface with the planet, this planet, if we want to understand who we are and what we are and where we came from, if we want to someday to be able to have the right kind of economic activity and unbelievable activity off Earth, if we want all those things to happen, we need to be explorers, and we need to be inspiring the act of exploration. Well, these are both fantastic projects, and so I can tell you the true inspiration for some of these things that we've been doing. It goes back to actually the movie Avatar. Who saw that? So do you remember what the Sigourney Weaver character, when she was in the transformed form of the alien, was wearing as her shirt? What did it say? Stanford. And I said, damn, that's not going to be the case. It's going to say... that shirt in the future, and all those shirts are going to say ASU. So welcome.
All right. Thank you, Michael. Inspirational as always. And so our next speaker is Thomas Truebuchen, Associate Administrator at NASA Science Mission Directorate. Thomas.
I think my claim to fame is I was the first one to know that those are the missions we're going to fly. I selected them. So what I want to talk about is really two things. The first one is just the mechanics of the Discovery program and how exciting that program is. In 1992, it was invented because it was really thought that what we should do is two things. First of all, we should fly more often into the sky, do the kind of discoveries that we're doing here, kind of explore other worlds. And the second one is that we should do so by building partnerships that otherwise we didn't. Enhanced partnerships with industry, enhanced partnerships with academia. And of course, the result of it is some of the best stories, some of the best discoveries that we've had, kind of missions that have changed lives, including my own. I was part of Messenger for a large fraction of my academic career. And so that's what the Discovery program is about. There's a series of missions that are flying right now, some of them that are getting ready to be launched, including going to Mars to do seismology, again with our friends from JPL, and in this case with foreign French contributions and so forth. But there's other missions that are just starting, like the two here. So that's really exciting. So that's the first thing I want to talk to you about. The second one I want to talk to you about is about how this affects the world. Just like 2/3 of the students at Arizona State, I'm the first one in my family to graduate from college. And so what can happen with this kind of mission, what can happen with the work that occurs at Arizona State is lives can be changed. Lives can be changed to do things that they could not even dream about. See, universities are not about achieving a goal that you come to school with. It's a coming up with new goals that you never thought about that are possible to achieve and getting there. That's what that is about. And so for me, one of the key elements of this, we see all these artistic views out there. The one thing I'm going to guarantee you right now is the real nature is way more beautiful than the best artistic view that we can do. And this is one of the things very much aligned with you, President, is kind of the event that occurred to me just before I left Switzerland. That's where my accent is from. No, not everybody speaks like that in Michigan. Or in DC, for that matter. So I left my town where I grew up in the mountains. Most of them are farmers, way more cows than people in the town that I grew up. And I basically volunteered to be a firefighter, just so I got to know the people. And so I remember it took close to a year working with the colleagues there, very hard workers, great people, just some of the most trustworthy individuals you could possibly meet, none of them educated at a university. And all of a sudden, they came to me one evening under the starry sky in a Swiss mountain village and basically said, tell us why you're studying physics. We'd like to understand. And I turned over and I said, you see these stars? What do you see when you see this star? And I pointed towards one of them and I said, well, just a star. I said, hey, it's not a star, it's a planet. And in fact, a planet, it's so hot on that surface that lead melts. I know that because I learned that. I learned more about nature than you could have ever imagined looking at that star. Do you see that other star? I pointed to one and explained to it. I said, you see that? What do you see? A star. What I see is a gas cloud that just exploded. And it's a gas cloud that over time may turn into a next generation of stars. That's what I see with the education I got. I remember the discussion we had and the discussion we had many times after about how beautiful nature is, because we all relate to that. We are explorers. You talked about that. We are learners. We are there and recognize, no matter what our educational level is, how beautiful nature really is, way more beautiful than we can imagine. It's going to be amazing. Now, what's really exciting about having colleagues and partners here at Arizona State University is that the goals that we have about enhanced partnership are very much aligned, and the educational goals that you talked about with the university are very much aligned with the goals that we have at NASA. I do believe that one of the biggest challenges we have at NASA is to retool our tremendous agency for the future, get talent in here that not only can do what we can do today, but excel beyond that. It's always about that. It's not about achieving what we did in the past. It's going to go well beyond that. That's what we're about. That's where we want, talented students from here, postdocs, grad students, to join us through these missions and in partnership through classes that you're going to organize as part of these missions, just accompanying it and really getting really this deeply inclusive workforce to really be part of what the future is going to be at NASA. So for me, the only thing I learned doing this for a long time is that none of us is good enough to do this by ourselves. All the problems that are worth doing are problems that we do together with others. And that's one of the things I'm going to see here, and I look forward to seeing. It's coming together with a tremendously, some of the best leadership team, scientific leadership team that I could possibly imagine. Just tremendous quality in, our PI here, the PI of Lucy as well, and the industry team, the NASA team that joins, together with the science team and these students, these young professionals that are going to grow as this mission is being developed, to coalesce into a team that can excel anything, go beyond any boundary that they currently imagine they can do. It's all about that. go beyond what we imagine we can do today and build a future that allows us to see nature in entirely new ways. That's what we're going to do right here at Arizona State University and with all its partners. Thanks so much.
Thank you very much, Dr. Zurbuchen and Crow. And now, before we move on to the panel discussion, where everybody will have an opportunity to ask questions, I'd like to ask you to direct your attention to the screen where we will see a short video on the Psyche Mission.
Psyche is both the name of an asteroid orbiting the Sun between Mars and Jupiter and the name of an ASU mission to visit that asteroid. The Psyche mission, chosen for NASA's Discovery program, will allow humankind to visit a metal world for the very first time. The mission plan calls for 20 months spent in orbit around the asteroid, mapping it and studying its properties. Psyche orbits in the outer part of the asteroid belt, about 3 times farther from the Sun than the Earth is, and Psyche is roughly the size of Massachusetts. The asteroid is most likely a survivor of violent hit-and-run collisions common when the solar system was forming. What gives Psyche great scientific interest is that it appears to be the exposed nickel-iron-metal core of an early planet, one of the building blocks of the Sun's planetary system. Terrestrial planets like Earth are thought to have metallic cores, but because their cores are unreachably far below the planet's rocky mantles and crusts, we cannot see or measure them directly. So Psyche may be able to tell us how Earth's core and the cores of the other terrestrial planets came to be. This mission, visiting the asteroid Psyche, will be the first time humans will ever see a planetary core and will help us gain insights into the metal interior of all rocky planets in our solar system, including Earth.
All right, thank you very much. I would like to ask the distinguished members of the panel tonight to step up and take their seats. I will introduce them for all of you. We have Lindy Elkin-Stanton, Director of the School of Earth and Space Exploration and the PI of the Psyche Mission. Yes, please. Phil Christensen is a Regents Professor, also in CC, and is the Lucy Mission's Thermal Emission Spectrometer PI. We have Jim Bell somewhere, also a professor in CC, is the Psyche Mission Deputy Principal Investigator, and a Lucy Mission co-investigator. Dave Williams, Associate Research Professor in CC and Director of the Ronald Greeley Center for Planetary Studies and a Psyche Mission co-investigator. Henry Stone, our guest from the Jet Propulsion Laboratory and a Psyche Mission Project Manager. And finally, Peter Lord, Space System Loral Deputy Program Manager. Okay, so then you can prepare your questions. I think I will start with a few questions I have prepared here, make sure that things get properly engaged, and then as you have your questions, I will be calling. There will be runners that have microphones around that will be brought to where you are. So you raise your hand, I will see you and direct one of the runners to you. Wait until they're where you are in order to make a question that can be heard by everybody. So let's see. I think I had some original questions here, and we can start anywhere we want. But is there perhaps a burning question from the audience that we could start with? No? Then I have mine here. So let's start perhaps talking about the Lucy mission. And so what are we hoping that Lucy mission will tell us about the early solar system, and why do we have to go to the Trojans to do so? So maybe we could have
You want to take this?
Dr. Christensen can take that on.
Thanks, Farhan. So as Farhan mentioned, Lucy is going way out to Jupiter, to this very unique cloud of asteroids. What makes them unique is, unlike many of the asteroids, they're very primitive. They probably have never been closer to the sun than Jupiter. They're the original ice and organic compounds that condense out there. So many of the asteroids that we study, including the one that we're going to with Osiris, have been close to the sun. They've been heated, they've been baked, they've been processed, they've been modified. And these objects haven't. They're truly pristine, and they're truly very rare samples of the early history of the solar system.
All right. So in order to do this, ASU's part will be to build and eventually use this thermal emission spectrometer. So can you tell us a little bit about the principles on which that works, the instrument, and what kind of data do you obtain and how it is interpreted?
Sure. I've been an infrared guy since I was a graduate student, and TESS is the thermal emission spectrometer. It's the culmination of a very long series of instruments that we've been building. One of the things I wanted to say was this really represents, for me personally, really the culmination of a very long career. I first came here in 1981 to be a postdoc with Ron Greeley, and Lucy Latesse is our ninth instrument that we've built. What makes it unique is that we're building it here on campus. And so that, to me, the capability, the potential, the ability to put together a team of people here is really phenomenal. The support that we've had over the decades really has allowed us to do something really special. TESS measures infrared light. We break that light up into a spectrum, sort of like a prism would. And in the infrared, every mineral has a very unique signature. And so we use that to get at composition, we use that to get at temperature. So we're trying to use those basic properties to figure out just more about these objects.
All right. So you mentioned that one of the important things that you like about our capabilities is to be able to build those instruments on campus. So are we involving students in the process? And because that's a magnificent way of attracting students and young folks to science and engineering. And so,
absolutely. I mean, the first instruments we built, they were built in California. And we had the idea and we ran them from here, but they were built in California. And it's been my dream for 30 years to be able to build them on campus in a room with glass windows that students can walk up to and see us building those and ask, what are those people doing? How can I get engaged? And so I'm constantly being asked by students, how can I be part of your team? How can I work with you? Of our team of 27 now engineers who are part of this group, 10 of them are ASU graduates. And so we've engaged as many as we can, but just sort of letting students see, hey, this is going on. I can see this. I can experience. Maybe I can participate. I can't imagine doing this anywhere but at a university.
That's great. Any questions for from the audience for Professor Christensen or about the Lucy mission? Anything burning over there? I think I see a raised hand over there. Yeah.
How many different Trojan objects will you approach, and how close will you get to them?
The current plan is to go by 6, sort of on opposite sides of the solar system. So it's a very long mission. We go out to Jupiter and then off to the other side of the solar system. But the plan is to go by 6. The problem with a tour like this is you're going very fast, and so we'll have a very short encounter. But with many of them, we'll get within 10 or 50 kilometers of those objects. So it'll be short, but very exciting.
One of the cool things to add is that 2 of those 6 are in orbit around each other.
Yeah,
It's a binary asteroid, and we've never seen one of those up close. And so that's going to be totally new and exciting too.
So you know exactly which asteroids in the Trojan you're going after. Because I was looking at a picture this morning. There's like thousands of them. And they're like in 2 families. Are you visiting the 2 families or just one family?
Yeah, we visit both families. Like I said, take your vitamins because it's going to be a very long mission.
And we fly by a main belt asteroid along the way.
That's
with
true.
a very unique name.
Better talk
Why
about
don't you
that
say
one.
some more about that?
Well, it's named after Don Johanson, right there, to commemorate the discovery of and all the the work that was done on Lucy and our early origins. So I think that's just spectacular.
Yeah, talk about progress, right? From the plains of Ethiopia. Took her 3 million years, but it came to SU, and now she's going to the Trojans. So that's progress. All right, any more questions? Yes, I see a couple of hands up there, and one there in the center. Next.
So with Juno being one of the farthest away operating spacecraft to use solar panels, I noticed that the Lucy model, which should be the same distance out there away from the sun, is using a different type of solar panel array. Also, that's got to change the way that you're taking thermal pictures. Can you elaborate on the sun's distance?
Those are very good observations. Yes, we are using solar panels. Yes, it's a huge challenge. Yes, they're huge. Yes, we have very little power to work with. Yes, it's very hard to take infrared images with very little power. You sort of hit right on the head there. But don't tell Thomas about these problems because we.
All right, so, there was another question right there in the middle. Did you get your microphone? Okay, just hold on for a second.
Do you expect to find similar compositions using the thermal spectrometer of each asteroid?
Yes and no. The problem with the thermal spectrometer, these objects are incredibly cold. And so our main job is to measure the temperature. We'll try to get the best spectra we can. We're hoping that those spectra will be good enough that we can distinguish compositional differences. What these missions do, and we need to let the Psyche folks on.
No, it's good. You're not sanctimonious at all.
But I am going to start lecturing you. Where was I? The spectra are going to be right on the edge of what we can do to distinguish. But what you try to do with these missions, you take visible and near infrared and thermal and as many different measurements tools as you can, because we have no idea what we're going to find. And so the hope is that by having this suite of instruments, you'll be able to tell how they're different.
Okay, so perhaps we can ask something as a segue to the Psyche team. You guys have a thermal spectrometer in your payload?
No, that's a sore point to fill too.
Well, there's a limit to how many thermal No, actually, we don't. That's really all I have to say. We don't.
You don't need one. I mean, it really would be the wrong technique.
Exactly.
Well, so we really went over this on the team. We had a long discussion about it. This is part of the exciting process of putting a mission together, trying to figure out exactly what measurements you need to make to answer your science questions when the kind of measurements you can make in space are very limited. And so it took a big discussion and some hard decisions because really any mission that has any kind of self-respect flies one of these instruments. and we got it. I'm just saying that. And we got a lot of pushback about this, but. But the truth is that kind of instrument measures identifies mineral species, and what we really need to know is elemental percentages. And so we went with a different instrument, a gamma ray and neutron spectrometer, and it was a hard decision, but there we are.
All right, well, sorry to cause trouble here, but, but so let me ask you an easy question now. So perhaps Linda can answer this question. So what makes the Psyche asteroid interesting, a great place to go and investigate?
This is so much fun to talk about because it only took us a few months to decide that of all the places we could go in the solar system, this was the one we had to go to. And so I said this in the video that this is the first time humankind will ever visit a metal world. We've visited all these worlds made of rock and with ice and with gas, and we've never visited a metal world. And we've never seen Psyche as more than just a speck of light in an optical camera. And so it's going to be a new experience. And it turns out that there is only one fairly large round metal world in our solar system, and it's Psyche. There's just one. So it's unique, and it's really special, and it's truly exploration because we don't know what we're going to find. And I can only hope that Thomas is correct and that what we find is even more beautiful than what we've imagined. And I wonder if, Jim, do you want to add anything? Dave, you want to add anything to that? Why we need to go? What's special about it?
Well, I think, first of all, I agree with the assertion made earlier that it was a bold choice of missions because, you think about it, there aren't many classes of objects left in the solar system where we've never seen a single one up close. And metallic asteroids, one class. Strange and bizarre Trojan asteroids, another class, right? And we're going to check those two off in the 20s with these missions. And, it's fun to engage artists and try to get fanciful and all that, but I think you're absolutely right. The reality is going to be stranger and weirder, and we're going to rack our brains and write great papers,
We're
right?
going to write great papers.
And figure out what these places are like. And Dave and I are involved in the development of the Imager, and we'll be getting these pictures down right there, around that corner, behind the glass wall here at ISTB4. And you tell me, what does impact cratering look like on a metallic world, right? What does tectonism look like on how do you take a planet made out of iron filings and create geology there? What's going to happen? What are we going to see? No idea. And if you're kind of wandering by those windows in N years, and you're going to scratch your head just like we are. It's like, what are they seeing? What is going on? And it's just going to be a blast to figure it out. Yeah.
All right. Follow-up questions from the audience over there?
I was wondering if there's something about the launch of single payload.
Yeah, I wonder if Henry, can you take that for the Psyche mission?
Sure.
And could you repeat the question for the audience? Because I think...
Yeah, the question was, where are we launching from and via what means? Well, the plan is to go out of Kennedy with an Earth-based launch. We're not going off from the space station or anything like that. We'll use solar electric propulsion to take us after 2 gravity assists. We'll do a Venus gravity assist, a Mars gravity assist, and then solar electric propulsion to take us all the way out to the Psyche asteroid. And then once we get there, we will go into 4 consecutively smaller orbits that allow us to zero in and take the various measurements that we need from the 3 instruments, primary instruments that we'll be carrying. And we go through that. It's very much like the Dawn mission did around Ceres, where you go through these steps of going down because we really don't know the gravity. You saw a really odd-shaped body, so we don't know the gravity properties very well. So we'll study that during the first orbit and calibrate that effectively to allow us to then drop into these lower and lower orbits, eventually getting to about 30 kilometers above the surface, which is really where the GRNS instrument, our gamma ray neutron spectrometer, will be able to go in all its full glory to make the elemental composition measurements that Lindy was talking about earlier. And on the way down, we'll be using the other instruments to study the magnetic field and the magnetic properties, and the imagers, of course, of Jim's to map out very carefully the topology. And then that'll provide the basis of the science data set that Lindy and the whole science team will go off and do the incredible magic that they do.
There's a question here up front.
I'm from Saguaro High, and I've never really seen Arizona as a particularly academic state. So I'm wondering what made you guys decide to have ASU as your hosting site for your missions.
Can I start with that?
Yeah, you go ahead, Dave, and then I want to say something.
Just because I've been at ASU since a long time, when I came out here for graduate school in 1989. ASU is one of the top 5 schools in the world for doing research in planetary geology and has been for, 30 years now. And it all goes back to the Apollo program and the preparation of the astronauts to walk on the moon. And work done at the Astrogeology Science Center up at the U.S. Geological Survey in Flagstaff helped train those astronauts from our geological sites here in Arizona. And then as the first samples were returned, part of that sample analysis was done by one of the professors here at ASU, Carlton Moore, who founded our Center for Meteorite Studies. And then in the early 1970s, the Department of Geological Sciences decided to bring in and make planetary geology a part of Arizona. And that's when my mentor, Ronald Greeley, was hired, along with Mike Malin, who's now in independent industry and who's building the camera for the Psyche mission.
You mentioned that Cindy's here, too.
Yes, and Cindy Greeley is right out there.
There she is.
So the short answer is, Arizona has a long history in planetary geology and planetary science, going back to the beginnings of space exploration. And it's something that we all here are very justifiably proud, our role in all of the various missions that have gone on since then.
I'd take it a step further, Dr. Williams. If you combine the sort of academic firepower in astronomy and planetary science and geology here at ASU with that at UA down in Tucson, and with that at Lowell Observatory in Flagstaff, and the USGS in Flagstaff, and NAU in Flagstaff, this is the greatest concentration of expertise, I think, in the world for the kind of work that we do. So Arizona is right up there, number one.
So, not many states can claim to have named the planet and then have to have had fight for it to keep it.
Yeah, and the fight continues.
So anyway, let me extend an invitation to the kids at Saguaro High and its principal to come to ASU, and we will be happy to show you what we have, not just in space science. Any other questions over there?
NEOCAM, the Near Earth Orbiter Camera.
I'm sorry, could you repeat the question for the back, please?
Yeah, I'm sorry. So the question was, how are we going to use data from NEOCAM in our missions? And so NEOWISE is the one that's flying now, right? And NEOCAM has development money. And so looking at near Earth objects is unfortunately not totally pertinent to what we're going to be doing at Psyche, except in that we will be looking at all the data that there is about metallic objects, including whatever's been seen by NEOWISE. I don't know if someone wants to add something about
just add that there are lots of new mission opportunities coming along, and a lot of us here are interested in small bodies and
absolutely.
The opportunities for proposing small missions, CubeSats or other small sat missions, and near Earth objects are going to be a prime place to study. So I think it's just going to help us all in the work that we do.
Hi there. So I have two questions. The first is, so in Earth-based laboratories, when you want to know the elemental abundance of something, typically you use an instrument that measures X-rays or electrons. But as mentioned previously, we have the grand instrument for Psyche, which is going to use gamma rays and neutrons. So what is the advantage of those two detectors over terrestrial laboratory equipment for planetary applications?
We're measuring what's available to be measured. That's the answer. So you can orbit around something and you can measure the output of the gamma ray interactions with the surface and neutron emissions. And this is actually going to be, for those of you who are space geeks, especially interesting for this instrument, because the neutron emissions are expected to be extremely higher than we've ever seen at any body because of the metallic nature of Psyche. And so I think that's actually going to be pretty exciting.
And then the second question, how does planetary protection work for a metal body?
The same as it works for any mission, we write to the Planetary Protection Officer and discuss with her, and she gives us our letter. Because so far, there's been no life discovered that we could imagine lives on an airless metal body. And so let me not ever plant into any of your minds ever that we could find any life there. It's not going to happen. Because if I thought it was, it would be really hard for us to run this mission.
So one of the aspects perhaps that I could bring in that we haven't discussed, and we were reminded before in some of the speeches that missions now, and I guess since their inception, are really teamwork. And we have here not just ASU, but some of the partners that came together in order to probably in both missions. But for the one we have guests here, maybe we can, Lindy, or maybe you can gloss over a little bit what that process is of bringing all the members of the team together, and perhaps we can hear a little bit about their experiences in working with our team.
Let me say a little introduction then for Peter Lord, who's here from Space Systems Loral. So one of the things that happens when proposing a mission is you need to choose an industry partner who's going to build a large portion of the spacecraft in collaboration with our NASA team at Jet Propulsion Laboratory and with us here at ASU. And so it's like a regular contract. You put out a request for information, and the usual suspects come and give you a presentation. You know, is it Lockheed Martin? Is it Ball? Is it Orbital ATK? And you know, there are a series of companies that normally did this, and we were very excited to get a response from Space Systems Loral. Like for ASU, I believe this is your first deep space mission. And we were worried from the beginning that this actually could be our choice of Space Systems Loral to be our partner, which we believed very deeply was exactly the right choice for our mission. This is a company that is absolutely the world's expert in exactly what we need. But because they'd never flown in deep space, we thought we could be dooming our proposal right with that decision, even though we knew that it was the right one. And part of the reason we also knew it was the right one was because they brought their A-team. From the very first moment, we felt such a sense of teamwork, such a sense of collaboration. And for a while, Peter Lord here was the only person working full-time on the Psyche mission in the world. In fact, he was the first full-time person. So Peter, can you tell us more about SSL and your experience with us?
Since the first, 3 years ago, that first mission, first meeting and the partnership, we recognized the challenge, you know, SSL, what do? They build geocom satellites that don't go anywhere into deep space. Their job. I say that because the engines that you see in Star Wars, the Hall effect thrusters, the glowing ion engines, those are the engines, the very engines we'll be using. And literally their job in most of our geosynchronous spacecraft is to not go anywhere, to keep them on station. We've been flying those for 10 years, and they're very economical, they're very reliable, and they're very low cost. We have now tripled their power, so for the first time, and we can harness that to now go places and to take something that it's the bedrock of something we've built over and over, and to be able to use it to provide transportation, to enable the exploration. Our job is to get this team of people there to provide the distance in the exploration. That's very exciting for our company to take that product and be able to see it doing something this exciting. And hopefully, I'm excited as a taxpayer. This lowers the cost, hopefully, to NASA of exploring the solar system. It's a different paradigm. We are doing this. Here's the really challenging part. Once we've got the agreements worked out, we've committed to do this on a firm fixed price contract. That is very unusual.
It's very unusual.
And this kind of a mission for a company, SSL, to say, you have designed the requirements so well, and we trust the parameters and everything are so well designed, we know we can do this. And we're excited to be able to step up and make that happen.
I think this is a great new kind of partnership for NASA and for American space industry. Really, I'm really excited about this.
We are too.
All right, we have a question over there from gentlemen.
What sort of propellants are used in these long distance missions? And how do you make sure you're going to have enough?
Sounds like Henry.
Really good planning.
Yeah.
And are you making it in the back? Is there a room in the back where you make this stuff?
Yeah, well, actually, what's kind of interesting about this mission is that we have the Hall thrusters will be run off of xenon gas, but we're also going to use xenon gas for the cold gas thrusters. So there'll be no chemical propulsion on this mission at all. We're only carrying xenon, which is quite new. And these guys are the experts in this area. So in terms of making sure that we have enough propellant, I'm going to rely on my buddy here to make some really good calculations.
We're actually making the deal with tanks full.
That's right.
So we buy a lot of xenon because we fly a lot of it. It's relatively abundant. It's not hard to get. The trick is running it through the right kind of electric engines.
That's right. And, you know, it turns out on this particular mission and using the bus that they already have and the characteristics of the trajectory we want to go on to get there, that we'll have plenty of margin in terms of the amount of fuel we'll be able to take with us.
It doesn't burn. It's an ion engine, and so it's an ion. The xenon is placed in a magnetic containment field, highly charged, and so the protons are separated from the electrons. Those protons are very dense and very heavy. If you look up Xeon in the periodic table, you see it's a very dense nucleus. So it's an ideal object, it's also neutral in that state, to put through a magnetic field and accelerate. That's exactly how this works. The Hall effect is a containment theory developed by the Russians for this type of thruster. And literally, if you've watched Star Wars and you've seen that blue glow, when you look in the test chamber, you see this plasma glowing and that same cobalt blue. I think that's a very cool part of it. Every time I see these engines,
I know, me
wow,
too.
these things, they're real, and we're going to use them to get out to Psyche. They are very low thrust. While they're very efficient at using that proton, this will take many years of very low thrust. The thrust being produced is about the weight of a quarter at best.
Right. But they're on all the time.
A lot of quarters. Right, Thomas? A lot of quarters.
There's a question up front here. So wait for the.
What is the total cost of the mission and how is it being funded?
I feel we should turn this to Thomas for the total cost of the mission. So he's throwing it back to me. So the way that these missions are proposed is NASA phases the missions A through F, and the requirement was that our phases A through D, which gets you up to launch, should have a cost cap of $450 million. And it is funded through taxpayer dollars. And as I'm very fond of saying, every penny is spent here on Earth with human beings for jobs and technology and things that make our lives better as we make this space mission go. And in terms, and can I just be hyperbolic for one moment? I really feel like this kind of exploration and this kind of courage to do these things that NASA does, its purpose, beyond the obvious, its greater purpose is to inspire everyone on Earth to take a bolder step, to take a bigger step, to do something that's really hard. And Jim, the total percentage of NASA budget of our national budget is
0.4%.
0.4%.
Yep. And those were the rules. That 450 was the rules, and it was a competition. 28 teams competing against each other, and 2 were selected. Yep.
That's right.
That gets us too long.
Then the rest of the budget will be spent. We don't have the total number to give you tonight.
Yeah, the Phase E operations port varies from mission to mission as a function of, you know, how long you have to be out there, et cetera. So we go through a separate discussion and negotiation with NASA on what will be needed as a function of how long the actual mission needs to take.
It's not going to be
to get to its target.
It's not going to be billions of dollars.
No.
It's a small delta on top of that.
Yeah. One little interesting side note, yes, it is, the $450 million was the cost cap up through the launch for the development of the spacecraft. But we also took the opportunity on this mission to, for some additional funds from headquarters, to be able to fly a technology experiment as well for technology development, which is the deep space optical communications, which is something that NASA is very eager and interested to be able to prove out. And this will be a flight to do that, and it's a great opportunity because we're going so far out. You'll be able to communicate and do tests all the way from just after leaving Earth all the way out to 3 AU to demonstrate that we can communicate by a laser light shining back and forth from the spacecraft to Earth. And so that's another thing that the mission will achieve.
Ma'am?
So I'll preface this by saying I'm sorry that we're still having this conversation 30 years after I studied science and technology in college, but this is directed to Lindy. What kind of participation are we seeing by female scientists in these kinds of projects?
Yeah, well, there's me. Yeah, no, so this is incredibly important to all of us, and it's not just lip service. I actually think NASA, and it's not because I'm here in public talking with everybody here, NASA's really working at this. And so of the 5 finalists in the Step 2 proposals for this call, 4 of the principal investigators are women. And our team, we have a lot of women, we have a lot of underrepresented minorities. I would like to introduce you to Carol Polanski, who's our project scientist. This is a very senior role. It's a very senior role, and in the hour before this, we were talking about our school, and we're working incredibly hard on this. And it's not just women, and it's not just underrepresented minorities, but it's anyone who feels that they weren't able to have their voice heard as they were coming up through, anyone who wasn't bred to the mold. And so it's a new world out there. The very first woman to lead a deep space mission was Maria Zuber. I think I'm the second. Maria is now the Vice President for Research at MIT. And so there's a lot going on. We're really working on this. And part of it is creating a culture where people can succeed on their merits. And we're all working on that. Thanks for the question.
Okay, so unless there is a burning question, it really has to be burn very hot.
It is, look at that.
His hand's way
It's
up
like
there.
Perhaps the
xenon.
last person over there who has the mic.
My marching orders have been if Psyche funding is impeded or harmed in any way on Capitol Hill, don't come back to ASU. So as the chief defender on Capitol Hill, why would policymakers want to be gung-ho about supporting this, and is there any correlation with commercialized space?
Yes. These missions are chosen strictly for science, and the science is very clearly delineated as something that can be answered with our instruments. But this will be the first mission that will go and see the surface of a metal asteroid. And it is a precursor for commercial space, and it is showing us the future of where we can go as a species. I did a little simple calculation of what the metals are that are in Psyche. It's Henry's laughing because I've embarrassed him with this before. But listen, this is true. So Psyche is made of iron and nickel, and it's made of copper and palladium and platinum and iridium and rhenium and cobalt. And when you multiply out how much of that there is in Psyche by the metal market prices that occurred on Earth in January, you discover that Psyche is worth 100,000 times the gross domestic product of the Earth. Or $10 quintillion, a quintillion, as Michael Crow reminds me. One of these days, we are going to be out there mining asteroids, and we're going to be mining them for metals, and we're going to be mining them for water not just for drinking, but for propulsion. And before we can go and prepare to mine things, we've got to know what they look like, and we've got to know what they're made of, and we've got to understand the shapes of their surfaces. So this is absolutely a commercial precursor mission.
Yeah, and former Congressman Salmon, I would remind you this is also fundamental knowledge, right? And that's your colleagues on the Hill appreciate all that stuff. I mean, you go to the textbook and you open it up to what does a metallic asteroid look like, and what do you get? A little dot.
Yeah, a little dot.
Well, we're going to fill that in, right? And all the things that, like Dave was pointing out, we've been doing the past 40 or 50 years is filling in the textbooks. What's around us? What are these worlds like? Let's all learn together.
Henry.
Well, I think you should also, we're teaming with SSL, a new partner, that does commercial space, and bringing them into this arena as well. And I think that bodes well for the future of further commercialization, kind of for NASA, expanding the base of commercial companies that are, interacting in this arena. So I think it's a tremendous opportunity. We're really looking forward to it.
Yep.
Okay, so that was the burning question that we had reserved for the end.
That's a great one.
And so I'm not going to talk about what the effect of bringing Psyche over in the metal market would have.
Yeah,
if
we
brought
don't wanna
all
bring
that
it back,
metal over
actually.
here.
Yeah,
So
there'd
we'll
be an
just
effect.
leave that for the poster signing session that is now. And let me remind everybody, we have also dessert for everybody out in the lobby. So thank you very much for accompanying us tonight. Thank you to our wonderful panel, our speakers tonight. Everybody have a wonderful evening.